Welcome to lecture number 21 for ECE 476, Advanced Embedded Systems. In this lecture, we're going to look at using a Raspberry Pi Pico to measure temperature and using recursive least squares to estimate the thermal time constant of a coffee cup. Now, a little bit of background. This is a course on Bison Academy. This is a website that has quite a few of the online courses in electrical computer engineering at NDSU. If you go to 476, here are the different topics. The next couple lectures, we're going to be looking at different types of sensors. So the previous lecture, we looked at text files, how to record data to a file. And the next couple lectures, we'll look at measuring temperature, current, heart rate, wind speed, air pressure, humidity, acceleration, light, position, GPS, stuff like that. Different types of ways to measure different parameters using a Raspberry Pi Pico. And in terms of measurement, that's actually an entire course called instrumentation. You can easily spend the entire semester looking at how to measure time, temperature, pressure, flow, light, stuff like that using a sensor. Next couple lectures, we're just going to do a scattering of those. In this lecture, we're going to focus on temperature. Specifically, we'll look at two analog sensors, a thermistor and a TMP36, along with a digital sensor, a DS18B20. Now, for most sensors, you can get both analog and digital. Analog sensors were pretty much what's existed prior to about 2010, 2000. They're nice. The output is analog. You can read that with a voltmeter, oscilloscope. Microprocessors have gotten so small and cheap, however, that many sensors have their own built-in microprocessor. I'm going to give an example of that, the DS1820B20. That's the temperature sensor with a microprocessor, so the interface is through a binary communication. With these sensors, we're going to look at measuring the temperature of a cup of water, measuring the temperature of a light bulb as it warms up and cools off. And then with the temperature of a hot cup of water, we'll look at trying to measure the thermal time constant. So starting out, for analog sensors, with the Pi Pico, you can measure voltage directly. That's the analog input on the Pi Pico. If I use a voltage divider, I can measure resistance. And here the idea is if I have a known resistor R0, with a voltage divider, the voltage is R over R plus R0 times 3.3. Solving backwards, if I know the voltage, I can calculate the resistance. That's basically how ohm meters work. In terms of resolution, that's the smallest change that I can detect. With a Pi Pico, the smallest change you can detect is with a 12-bit A to D, 3.3 volts over 4095. The smallest voltage I can detect is 805 microvolts. So for a resistance, an ohm meter, the resistance has to change by enough that the voltage changes by 805 microvolts. If I start at something nominal, like 1,000 ohms in a voltage divider, I should get 1.65 volts. For it to change by 805 microvolts, the resistance has to change by 0.977 ohms, meaning this is an ohm meter that has a resolution of 0.977 ohms. Okay, so that's just resistance. Let's get into temperature. Now there's many different types of temperature sensors. You go to DigiKey, they've got thousands of them. Pick one, like here's a nice one, kind of picked at random. This is a thermistor. A thermistor is a piece of silicon. Silicon is a semiconductor. At 0 degrees Kelvin, all the electrons are tied up in covalent bonds, so the resistance at 0 degrees Kelvin is infinity, or the conductivity is 0. As temperature goes up, I create more and more thermal holes. Each hole that kicks up its covalent bond also creates an electron. Those are charge carriers. More and more charge carriers means less and less resistance. So in general, for thermistors, as temperature goes up, the resistance goes down because they get more and more charge carriers. At 0 degrees Kelvin, the resistance is infinity. Now the mathematical model for a thermistor generally looks like this. It's exponential in nature. And this is the temperature in Kelvin. So when the degrees Kelvin is 0, this is infinity. E to the infinity is infinity. Basically, it's an insulator at 0 degrees Kelvin. As temperature goes up, the resistance drops. The more terms you include, the better the curve fits. Typically, we just use a two-term model. So this is kind of what we used in quite a few of our classes. Good enough for what we're doing. I can rewrite this as a resistance and pull the A outside. E to the A plus, well, E to the A plus B is E to the A, E to the B. So pulling this outside, that's a constant. That's the resistance at 25 degrees Celsius. This is the second term. Instead of using Kelvin, I'm going to use degrees Fahrenheit, or degrees Celsius. So T plus 273 gives you Kelvin. To make it convenient, at 25 Celsius, this is 298. These cancel. E to the 0 is 1. This is the resistance at 25 Celsius. So that's just another way of writing this equation. This is typically what's used in thermistors. If you look at the data sheets, they'll give you the resistance at 25 degrees Celsius and a thing called B. That's a constant that tells you the slope of that exponential. So given those two terms, I know the mathematical model for a thermistor. If you look at the data sheets for a thermistor, you can pull out those two. For example, if you go to GeeekPi, here's that thermistor. If I scroll down, it's going to give you the resistance at 25 Celsius, gives you the B parameter, 3930, and actually gives you the full data sheets if you want. Once I have those two parameters, I can then calculate the resistance versus temperature and plot it. So here's what she looks like. Again, the data is at 25 Celsius, it's 1K. As temperature changes, the resistance changes. Now, resistance is hard to measure, but voltage is easy. So one trick is to add a voltage divider. In this case, if I use a 1000 ohm resistor, the voltage is going to be your 3.3 volts. Your resistor, here's your thermistor. Make this 1K, kind of arbitrary. That voltage versus temperature now looks like that. So if I know the temperature, I know the voltage. If I know the voltage, I know the temperature. And solving backwards, this is, given the voltage, how to calculate the temperature. In terms of resolution, that's the smallest change that will result in a 1-bit change on the A to D. Going back to 25 degrees Celsius, if R is 1000 ohms, the voltage is 1.65 volts. The smallest change in voltage I can see is 805 microvolts. The smallest change in resistance I can see is R goes from 1000 to 1000.97 ohms. Plugging it back into this equation, the temperature goes from 25 degrees to 24.977. Take the difference. That's the resolution of your temperature sensor. So with a thermistor, I can measure temperature to 0.02 degrees Celsius. All right, so with that, let's have some fun. Let's measure the temperature of a light bulb as it turns on. So what I'm going to do is I'm going to use a 10K thermistor. That's what I had on me. It's going to get warmer, so I'm going to make this a little bit less because when it gets hot, R is going to go down. Ideally, these should match at mid-band. The best sensitivity is when these match, and this is half your power supply. As I measure temperature, we'll save that, and the questions I want to ask is how long does it take the light bulb to warm up, and how hot does it get? So there's the hardware. In terms of software, I'm going to reuse the previous code for writing data to a file, change it slightly. I'm going to read in the voltage, calculate resistance, calculate the temperature, print that, and then save it to a file. So here's what that looks like. This is converting the A to D to voltage. The thermistor I'm using is 10K at 25 Celsius. This is the B parameter. This is my voltage divider, 2000 ohms. do the analog reading, well, once every second, read the analog voltage, calculate resistance, calculate temperature, and print it. So as I run this puppy, here's my data. This is the voltage, the resistance, and the temperature. As I warm it up, got my finger on it right now, you see the temperature is warming up. I'm also writing this data to a file. And here I truncated it. At 30 seconds it stops and closes the file. At that point I can open up the file. It's called thermistor LED. To file open from the Raspberry Pi. Thermistor LED, there it is. There's my data, time in seconds. There's my temperature. With that I can then plot that in MATLAB. Do whatever you want with it. Connecting that to an LED light bulb. It's one of these GE light sticks. It's a 60 watt equivalent light bulb rated at 10 watts. Measure it over 5 minutes. Here's the temperature of the light bulb as when you turn it on. You can kind of see that it's kind of noisy and it is warming up. So I am measuring temperature. If I let it go further, it would eventually flatten out, and that would tell me how warm the light bulb is in steady state. A couple things to notice from this. This looks like an exponential rise. It's like you're charging a capacitor. Charging a capacitor satisfies a first-order differential equation, basically the heat equation. That's what she looks like, and we're pulling off like this part of it. Not too surprising. Heat equation. Well, that'd be like a first-order differential equation, the heat equation, or something warming up. Second thing to note is the data is pretty noisy. Well, part of the reason it's noisy is I've got wires running from my sensor and the light bulb to the Pi Pico board. Those long wires act as antennae. They pick up RF energy, and you get noise like this. I could reduce the noise so that rather than having your temperature sensor right here and running 2 wires back to your Pi Pico board, make this a twisted pair wire. What the twisted pair does is the RF energy, it builds up, it generates voltage based upon the area between the two. The twisted pair keeps the area small, plus by twisting it, the voltages add, subtract, they pretty much cancel. So using a twisted pair wire would keep the noise down quite a bit. Even better would be using a shielded twisted pair wire. So add a shielding to it, ground the shielding, that keeps the electric fields away from the wires. Whatever does get in is pretty much canceled with the twisted pair. Basically, you don't want to keep long wires all over the place. They act as antennae. But anyway, that's what the data looks like. That's with a thermistor. The second type of analog temperature sensor is a TMP36. Now this is a sensor you can find on Amazon, find on GeeekPi. It's a thermal diode. Now, a property of diodes is the voltage drop across the diode depends upon the intrinsic carrier concentration. That in turn depends upon temperature. So if you plot the voltage drop across the diode as temperature changes, it's almost linear. Well, a TMP36 uses that to create a sensor where the voltage changes by plus 10 millivolts per degree C. So from the data sheets, you can see that this works at anywhere between 2.7 and 5.5 volts, meaning it works just fine with the Pi Pico at 3.3 volts. The output at 25 Celsius is 750 millivolts, and the sensitivity is 10 millivolts per degree C. So at 25 C, that's what I should read on the voltage. At minus 40 degrees C, 100 millivolts. At plus 125, 1.75 volts. So by measuring voltage, I can tell you temperature. That also gives you the resolution. The equation for temperature based upon voltage is just 100V minus 50. The resolution then is, I can see 805 microvolts change with the A to D. With that sensitivity, gives you 0.08. I can measure temperature to 0.08, feels about 0.1 degrees Celsius. In terms of hardware, it's actually pretty simple. You just connect it between power and ground. The middle lead is the analog voltage out that goes straight to the Pi Pico, and I can measure temperature. In terms of coding, it's really about the same as before. This is the previous code. Previous lecture looked at how to save data to a file. I'm going to read the voltage, calculate temperature, and save temperature to a file. What that kind of looks like is this. So here's your code as I run it. Well, here's the main routine. For 30 seconds, I'm using a timer interrupt to set the sampling rate to 1 second. For 30 seconds, there's the voltage, calculate the temperature, and display it. So here's the sample, voltage, temperature. I hold my finger over the sensor. You can see the voltage is changing. The corresponding temperature is changing. After 30 data points, the file is closed, and that was the name of the file. Open that on the Raspberry Pi 30. There's the data I just collected, time and temperature. Okay, with that, let's look at something else. Let's find the temperature of an incandescent light bulb. Now, these are the light bulbs your grandma used to use. They're a whopping 2% efficient. Basically, there's a thing called an Barbie Easy Bake Oven. You put a 25-watt light bulb in a metal box, and it gets hot enough you can make brownies, cupcakes, stuff like that. This is not a really great light bulb, but it's kind of the rage back in the 1950s, 60s. They get really hot. Let's find out how hot they actually get. Well, to do that, I would just take a TMP36, stick it on the light bulb, run the wires over your Pi Pico, turn on the light, and measure the voltage or temperature versus time. So when I do that over a span of 180 seconds, 3 minutes, here's what the temperature does. And this gets a lot hotter than the incandescent light bulb. It's a lot less efficient. Again, it's satisfying a first-order differential equation. That's the heat equation. It's still kind of noisy. Again, what I did is I just ran long wires. Where are they? There's the wires going to it. Not the best way of doing it. Those wires act as antennae, pick up RF energy, and that shows up as noise in your data. I could do better if I used shielded twisted pair wire rather than just stray wires. That would cut down the noise quite a bit. But anyway, I can measure temperature. Third type of sensor. Now, the previous two sensors were both analog sensors. The nice thing about analog is they're really easy to get to work. I can connect up the sensor, look at the voltage on a voltmeter, see that it's changing, connect that to the analog input of your Pi Pico. I can read it. And analog is pretty straightforward. The problem with analog sensors is you tend to have quite a bit of noise. I could reduce the noise by making the wire shorter. One way to do that is have the sensor tied right to a microprocessor, keep the wires really short, and then communicate with the digital interface for the microprocessor. That's what the DS18B20 is. This is actually a digital sensor, a sensor plus a microprocessor, all in a tight bundle with wires that then go out to the leads. These wires talk over a binary interface. Disadvantage is if you connect that up, power and ground, nothing happens. You need a microprocessor to query it to get the data. Advantage is you'll have much cleaner data. Now the DS18B20 has the following specs. You can buy these on DigiKey, Amazon. They're not real expensive. Here you get 5 for $10. They operate from -55C to +125C. Operate between 2.5 and 5.5 volts, meaning they work with a Pi Pico. And the resolution is 0.06 degrees Celsius. And each DS18B20 has a unique 64-bit serial code, so you can actually have a large number of these on a single bus and talk to each one separately. In terms of hardware, it's pretty straightforward. You give the sensor power, ground, the signal goes back to the Pi Pico. This guy needs a pull-up resistor. This is actually just either floating or ground. You need the pull-up resistor to convert it to voltage. And generally you need a 4.7K pull-up resistor to convert it. With the Pi Pico, you could also use the internal pull-up resistor. That also works. Once I do that, I can talk, if you have the right software. In terms of software, you can dig through the data sheets and find out how to drive it, or, oops, somebody else has done that. Well, it turns out with MicroPython, the DS1820 is already part of the library. So to use it, you just need to import two routines, one wire and DS1820. That's kind of built in with Thonny. I need to tell it, which pin am I talking on? I'm going to talk on pin 4. This is the name, the variable name of the sensor is the DS1820, using one wire interface on this pin. It will then scan, look for all the DS1820s connected to pin 4. Once it finds them, store them in an array called ROMs. Here I only have one of them connected. I can then read that sensor. I'm going to do a temperature conversion. When you do a conversion, you have to wait 750 milliseconds to get 12-bit resolution. I'll then wait 750 milliseconds and then spit back the reading and print it. So this is kind of a difference between embedded systems and advanced embedded. In embedded systems, we looked at low-level programming. That would be, how do you write these subroutines? How do I talk to the sensor? In advanced embedded, that's mid-level programming. Somebody's already written those routines. I just want to use them. So the procedure is, again, follow these steps. I can then read the sensor. If I run this program, I've got a DS1820 here. This is the ROM address of that sensor. That's the temperature in Celsius. As I warm it up, stick my hand over it. You can see the temperature is increasing. To set the sampling rate to 1 second, I could use the same trick as before, use a timer interrupt, so that every second it runs through this loop, takes a reading. It's a little bit inefficient, so as time runs along, it says 1 second's elapsed, start the conversion, wait for it to complete, read the conversion, print it. If I swap the order, since this is a 1 second sampling rate, I could say start the conversion, wait for the 1 second to elapse, print it, start the conversion, wait for 1 second to elapse. That would also work. When you display the temperature reading, this is actually the reading from the previous conversion. So the data is always like 1 second old. If I did that, I wouldn't have the sleep command in there. This burns up time, limits what else I can do with the Pi Pico. But kind of subtlety. I only have a single sensor, so this also works. I'm taking one reading every second. With that, let's do something. Like, let's measure the temperature of a hot cup of water. The DS1820 is a watertight sensor. I can stick this in hot water and measure the temperature. So doing that, I created a hot cup of water, stuck the sensor in it, and let it cool down. So here's cooling off over 30 minutes. Write the data to a file, and then plot it. So a couple things to notice. The data here is actually really, really clean. The reason for that is partly because the leads from the sensor to the microprocessor are very, very short. Once it's converted to a digital signal, as long as they can read the digital signal, I no longer have the noise problems. So I get much, much cleaner data. It's actually a lot easier to use. I just have to start the conversion, then read it. Once you have the driver routines, and I can now measure temperature of a cup of water. I can look at what's the temperature of what put a lid on it, what's the temperature if I had a spoon, does that koozie make a difference, all sorts of things like that. Now, if I want to come up with a number to parameterize this coffee cup, one thing I could do is model this mathematically. This is a decaying exponential. It's the T ambient right here at the room temperature. So what it's cooling down to. The exponential is a b e to the at. This is your thermal time constant. Minus 1 over a is your time constant in seconds. The bigger the thermal time constant, the flatter this is, the better the coffee cup. So let's estimate that thermal time constant. Well, once I get my data, I can analyze it. The time constant should be minus 1 over a in seconds. Tells you how good the coffee cup is. What I want to do is come up with the terms b and a to approximate my data. Well, the problem with this is I can do a thing called least squares, but for least squares to work, it's got to be linear in time. So take the log, bring T ambient left, take the log of both sides, and now have the log of T minus T ambient is AT plus B. That's linear in time. With least squares, I can estimate these linear constants. A and B. It's actually B times 1. The formulation of that is put this in matrix form. Here's my data, the log of T minus T ambient at each data point. Here is my basis function, time and 1. There's my constants. Find A and B to minimize the error between the data and my curve fit. The solution is if I treat this as y is b times a, multiply both sides by b transpose, invert b transpose b, solve for a. So this is the least squares curve fit. In MATLAB I can do that. I can take the data in the Pi Pico, save the data to a file, copy it, paste it into MATLAB, pull off the columns of data. Time is the first column, temperature is the second column, the room temperature, you have to know what that is. Form the basis function, that's t and 1, to least squares curve fit, and I get these terms. This is my thermal time constant, that's the slope, there's my offset. That's what I really care about. My time constant is minus 1 over a, so that is 31.68 seconds. And if I want to see how good my curve fit is, I can just plot t versus data, t versus my curve fit. And you can see it actually matches up pretty well. Now, least squares does work. It needs MATLAB, however, kinda. You're going to run into problems with the Pi Pico. You've got a lot of data to store. You're going to run out of memory. It's going to take a lot of computations. That's just using least squares. Well, there's a way around that. There's a thing called recursive least squares. I don't have to sit there and record all the data and recalculate your B transpose B inverse B transpose Y. I can solve that just a few matrices. So what we're going to look at next is recursive least squares, how to find the thermal time constant in real time. And when I do that, I'll be using all the data. Well, the time constant is changing. I might want to use more recent data more heavily, or weight that more heavily. So also look at recursive least squares with a forgetting factor. Now, recursive least squares is as follows. Let's just assume I've got 4 data points to make it manageable. I've got 4 data points. Find A and B. Least squares I do, this is called B, this is Y. It's B transpose B inverse B transpose Y. Well, if I multiply all this out, what I get is, first column times first row, the sum of x squared. The off columns are sum of x, and this is the sum of 1, which is just n. So that's your B transpose B. This is B transpose Y. And here's your B transpose Y. The first one is x0, y0 plus x1, y1 plus x2, y2. The second row is y0 plus y1 plus y2 plus y3. Same thing. So I don't really have to keep track of everything. I can just keep track of what's the sum of x squared, what's the sum of x, number of data points, the sum of x times y, sum of y. Keep track of those parameters, and I can calculate a and b. I don't actually need to keep track of all the data as well. I can make this recursive by saying that the next value of b is the old value plus xi squared, xi, xi1. The next value of y is the old value plus xi, yi, yi. This is the recursive least squares. The next value is based upon the old value plus an update. So now all I need to do in Python is just keep track of these matrices, update them every sample, and if I do B transpose Y, I can tell you what A and B are each sample. So here's what the code does. I'm going to start with the initial value. It should be 0, 0, but then I get problems with matrix inversion. So I just made it something small so I can invert it. Every second, I'll read the temperature, and then update. Take the old value b and add to it x squared, x, x and 1. The old value of y, update it with x times y and y. Invert b, inverse b, multiply by a. Those are your time constants, a0 and a1, for a and b. And I can update these in real time. So if I do that and plot the thermal time constant, that's -1 over a. That is units of seconds. Here's what the thermal time constant looks like. It is time changing. That means I have a nonlinear system. Part of the reason for that is the coffee cup I used doesn't have a lid, so I've got 2 ways to lose heat. Well, actually 3 ways. There's radiation, but that's kind of minimal at these temperatures. There's conduction, that should be linear, and convection. I basically have evaporation. The evaporation initially is fairly significant, and then it gets less and less significant as time goes on. Plus I have my initial value based upon my b of 0, y of 0. Anyway, that's what it looks like, my estimated thermal time constant. Well, one problem with least squares is I use all the data. So as time goes on and on, this last data point has a weighting of 1 over 1800 because it's just 1 point among 1800 data points, and so on. So the weighting for each data point gets smaller and smaller as time goes on. If the system is time varying, eventually I kind of ignore the changes. But that's least squares. A couple of variations on that. If I want to use a moving window, what that does is instead of using all the data, I'm just going to use this small piece of data. And as the window slides along, I will have an estimate based upon the last 100 data points. That's called a moving window. Well, to do that, I need to remember what were the last 100 data points. So it takes a little bit more buffer. I can then update my B and Y matrix. When I have the next data point, say at 100, I'm going to say what it was at 99, add data point 100, and pull off the data from 100 samples ago, because again, I'm ignoring that now. So the computations aren't too bad. I just have to remember the last 100 data points, update B and Y based upon the current data and the data from 100 samples ago. I can then calculate the constants by B inverse Y. So in terms of coding, I will remember the last 100 data points. There's my pointer, mod 100, so I'm using a circular stack. Update the data. I will just subtract the previous data point, then add in the current data point. If I'm past the 100th sample, then recalculate the data points, recalculate the constants, and then the thermal time constant is -1 over a. So if I do that and calculate the thermal time constants for the first 100 data points, there's no reading. I need to fill up the buffer first. I then get this data. Again, a couple things to note. This is a lot more noisy because I'm only using 100 data points rather than 1800. But on the other hand, it's also more responsive. As the thermal time constant is changing, my least squares curve fit will follow it. So that's least squares with a moving window. Another option is least squares with exponential weighting. This might seem harder, but it's actually easier way to code it. I'm going to use all the data, but the data gets discounted with a factor of alpha. So like if alpha is 0.9, I'll use the current data with a weighting of 1. Previous data is a value of 0.9, 0.9 squared, 0.9 cubed, and so on. So as I go back in time, the weighting goes to 0 exponentially. So my data, my curve fit, will be based upon the most recent data, mostly. Actually uses all the data, but the most recent data is more heavily weighted. That seems harder, but it's actually easier. So what we were doing is when I update b sub k, it was the old value plus the update. With an exponential weighting, I take the old value times weighting alpha plus the update. So alpha's number between 0 and 1, like 0.995. This is how much I forget the old data. Keep on multiplying by alpha, and eventually the data goes away, gets ignored. So this is actually a whole lot easier to implement. If I then try that, like with a weighting of 0.995, every sample, I discard the data by 0.5%. So when the data is current, I'm using the data with a weighting of 1. 100 samples ago, the weighting is 0.61, 0.995 to the 100th. 200 samples ago, 0.37. The weighting goes to 0 as the data gets older. In terms of my thermal time constant that I'm estimating, it's a lot smoother than before because I'm using more data. And it is able to follow the changing dynamics. For example, at the end, this is my least squares curve fit. It's matching the slope towards the end of the data. Ignoring the start, this is when I had more evaporation. Cooling down, there's less evaporation. Time constant's getting longer. So that's kind of least squares. With least squares, it's an easy way I can sit there and update my time constant on the fly. So if I'm measuring the time constant of a coffee cup, I don't have to sit there and wait to collect the data to analyze in MATLAB. I can calculate the time constants on the fly and display them on the fly. So kind of in summary, temperature is actually really easy to measure. You can measure temperature using analog temperature sensors, like a thermistor or a TMP36. I can measure temperature with a digital temperature sensor. Analog is kind of nice because the output is analog. Just look at it with a voltmeter. If it's changing, the sensor is working. A digital temperature sensor is a little bit harder to use. Connect it up, look at it on a voltmeter, nothing happens. You need a microprocessor to read it. If you have the driver routines already, like in this case, one wire DS1820, they're actually not too bad. Once I get the driver routines, I just need to call them, use them to start the temperature conversion, read the sensor, and I can get temperature readings with actually less noise because I no longer have the long wires running back to my Pi Pico board carrying analog signals. Once you can measure analog, you can do all sorts of things, like measure the thermal time constant of a coffee cup, temperature of the room, temperature of a light bulb, your pick. So that's lecture number 21 for ECE 476, Advanced Embedded.